All right, so let's talk about Lewis structures. Okay, we'll talk a little bit about Lewis structures because basically we're going to go into Lewis structures and then we're going to look at molecular geometry. That'll be the next one. And then we'll also look at the electron pair geometry. And then we'll also start going into hybridization. And then we'll also be looking at molecular orbital theory along the way. Okay, so let me start you off at just Lewis structures. Okay, Lewis structure in of itself is basically a 2D representation of a compound that we may be looking at or a molecule that we may be looking at. So there's a set of rules that I like to go by, and we can go ahead and start off with those. So the first rule that we want to deal with is number one is going to be find the central atom. And what you want to put in this is that what you want to say is usually the most electronegative atoms or the larger number of atoms are on the outside. Okay, so the example I would like to say is water. It's H2O, right? It has two hydrogens and one oxygen. Going by this, we know that oxygen is actually in the middle because the larger number of atoms is actually number one. So put a little one here, and then put a little two here. Okay, so number one, go by the large number of atoms. Number two, go by which one is more electronegative. Okay, so we know that oxygen is going to be in the middle. All right. What you want to do next is place the valence electrons around the central atom. Now, when we're doing this, the other thing that you got to keep note of is valence electrons. Valence electrons, or the outermost shell electrons, they're responsible for bonding. Okay, and that's what you want to remember about these, is that the valence electrons are responsible for bonding. Okay, so the way we can look at this is if we look at our periodic table. Yeah, I know. So if we have this, we can say that essentially this section is going to be one valence. This is two valence. Okay, then it goes three, basically 3, 4, 5, 6, 7. It goes all the way up to here. And then you have, it starts over with boron, boron, carbon, nitrogen, oxygen. And we're going to erase this point here. Erase this. Oxygen, fluorine, and then essentially we can go to neon, which is the noble gas configurations. Once we go there, what we want to do is take this, and this is going to be 3, 4, 5, 6, 7, 8. Okay, that is the valence. These are valence electrons. Okay, so we want to place the valence electrons. That was number 2, right? So we have our oxygen atom. Put this over here. We'll put a valence electrons, which is 6 if you look at your periodic table. Now the next thing is going to be number 3. Place the outside atoms around the central atom. In this case, that's hydrogen. 4. Place valence electrons around outside atoms. So 1, 1, 5, and there's like 10 of these. We're going to really mainly just focus on about roughly 8 of them, 7, 8 of them. So the next thing we want to do is make at least one bond to each atom. So make one bond, one bond. Now, what you want to keep in mind is that a bond consists of 2 electrons. Okay, I repeat, a bond consists of 2 electrons. All right. Now, this is called a lone pair. What that means is these are non-bonding electrons. I'm going to say that again. Lone pair is non-bonding electrons. All right. But any bond is going to consist of 2 electrons. So let's say, for example, if I have a double bond, how many bonds is that? That's going to be 2 bonds. How many electrons between those 2 atoms? That's going to be 4. What about a triple bond? It would be 6. Okay, that's how you want to think about them. Remember, a bond consists of 2 electrons. The next thing that we want to check is check the sorry, I'm jumping to that. Let's see. One second. Check the octet rule. So check the octet. All right, that's the next thing that you want to do. After that, which basically the octet rule is that says that for most non-metal species, you want to make sure that you have at least 8 valence electrons. Now, there are some examples that can go beyond 8 and some that can go below it. Some such examples would be P, S, Cl, Ar, and down. They can expand. They can expand beyond 8. All right. Far as boron and down, they can have less than 8. Okay. So keep that in mind when we're doing these. All right. So let's check it to another case. Okay. Say, for example, if we come across some species such as this, say CH2O. This is formaldehyde. All right. If we do the common thing, we have the carbon in the middle. We put our valences. It's 4. We put, now remember, I had to choose between these for our central atom. This is most electronegative, so no, that's out. This has the most, so this is also out. So that means that my carbon is going to be in the middle. So we have H, H, and this is O. If we put our electrons make at least one bond. Our octet is not filled. If we count, remember a bond is 2 electrons, so it's 2, 4, 6, and this is 7. Same thing after that. It's not gonna work. So we need to move electrons. So what you remember is that electrons are not finite. You can move them around. Okay, so let's erase this. And we'll put him here. And we can make this. What you want to do, this is number 7. What we want to do is, if possible, or rather you can say, if the octet fails, try a double or triple bond. Okay, now what you want to remember, do not make a double bond 2 boron, fluorine, as well as mainly those. Those are the biggest ones, actually, because you'll come across them and you will make double bonds, and that's not good. Okay, so you want boron and fluorine. Halogens tend to double bond to oxygen and sulfur, with the exception of fluorine. Okay. Now there's several other things that can double and triple bond and so forth, but those are the ones that you really, really want to look out for. Okay. So our overall structure is such: when we count electrons, everything works out. The next one, okay, number 8. If there is a charge, add electrons if negative, and take away electrons if positive. Okay, so what that means is that, say for example, what's a good one? Let's think about a good one. What about chloride? Chloride is Cl minus, right? Due to the fact that chloride technically has a valence of 7, but when we look at its overall, we see that it has 8 because this has a minus. Or let's say I have one with more chemical bonding per se. Let's say NH4 plus. When we draw this out, right, I should essentially have my 5 hydrogens here. I can make my bonds. Then I'm left with this guy. This guy needs to go. This is where the positive charge comes from. So we want to take away, therefore I'm left with positive charge. As such. Okay, and this is what we call ammonium. All right.